Here we shall consider the sequences whose members are real valued functions defined in an interval and distinguish between two types of convergence of such sequences. The first type of convergence is pointwise convergence. Suppose the fn n is equal to 1 to infinity is a sequence of functions defined on an interval capital I is equal to close interval ab. To each point small c belongs to capital I, that is close interval ab. There corresponds a sequence of numbers f and c with terms f1c, f2c, f3c up to f and c and so on. We suppose that this sequence f and c is convergent and each of this sequence arising for different value of small x belongs to capital I is also convergent. That is, the sequence of number f and x converges for every x lies in the given interval. Thus, we define a natural way a real valued function, say f with domain capital I such that its value fc for c belongs to capital I is limit of f and c when n tends to infinity. The function f thus defined is referred to as the pointwise limit of the sequence fn. Also, in this case we say that the sequence of function is pointwise convergent. So, if fx is pointwise limit of the pointwise convergence sequence f and x of functions defined in interval capital I, to each x belongs to closed interval ab and to each epsilon greater than 0 there corresponds an integer, say small m, such that mod of f and x minus fx is strictly less than epsilon for all n is greater than equal to m. That means if a sequence of function it is pointwise convergent and converges to a function fx, then the mod of f and x minus fx will always less than epsilon for all n is greater than some particular natural number. Problem first. So that the sequence of function f and x, where f and x is defined as f and x is equal to x to the power n for all x belongs to closed interval 0 1, is pointwise convergent on 0 to 1. So look at this sequence of function. If I put x is equal to 0 here, fn 0, we get the value 0, and when we tend n is equal to 1 2 3 4 5 we get value 0 0 0 0 0 and so on. So putting x is equal to 0 0 here and moving n from 1 to infinity, we get the first member of the sequence, which is 0 0 0 0 0. Again put x is equal to 1 here. Fn1 is equal to 1 to the power n. If Fn1 is equal to 1 to the power n, and for n is equal to 1 2 3 4 5 6 and so on, we get a sequence 1 1 1 1 1 1 1, which is also convergent. So as we have given fnx barabar x to the power n for all x belongs to close interval 0 to 1, and fx is equal to limit n tends to infinity fnx is equal to 0 when x is greater than equal to 0 and strictly less than 1, and at point x is equal to 1 we get limit 1, because at point x is equal to 1 we get sequence 1 1 1 1 which converges to point 1. Let epsilon be greater than be any positive number that is greater than 0. Then for x is equal to 1, fnx minus fx is equal to fnx. For x is equal to 1, fnx is 1, and the limit of fnx is also 1. So 1 minus 1 is equal to 0, and 0 is always less than epsilon for all n. For x belongs to 0 to open interval 1, fnx minus fx is equal to mod of x to the power n minus 0, and this implies x to the power n is less than epsilon. Now this implies x to the power n is less than epsilon because x lies 0 to 1 and in this interval x is positive. So we can remove the mod function here. Now taking log both sides, we get n log x is strictly less than log epsilon. Multiplying by minus sign both sides, this inequality change less than change by greater than sign. So minus n log x greater than minus log epsilon. Now shifting this minus sign, we get n log 1 upon x is greater than log 1 upon epsilon, and this implies n is greater than log 1 upon epsilon upon log 1 upon x. Now taking its greatest integer value, and we give this integer value name capital N. So for each x belongs to close 0 to open interval 1, for each x belongs to 0 to 1 and epsilon greater than 0, we get a natural number which value is equal to greatest integer value of log 1 upon epsilon upon log 1 upon x, such that mod of fnx minus fx is always less than epsilon whenever n is greater than equal to capital N. This implies that the sequence of function fnx is pointwise convergent, because for each x fnx converges to 0 when x is not equal to 1, and when x is equal to 1